All right. Good morning, gentlemen, and happy Tuesday. Today is Tuesday, April the 28th, and today we are going to continue our discussion of electromagnetic applications. All right. Again, this is one of those units where uh, if we were in school, I'd be able to do a little bit more and show you some more things. And it's not something that you would see in a typical high school physics class, but I think it's kind of important that you see how some of these things relate to the technology that we have in the modern world. So, in any event, today's lesson on electromagnetic applications is on electron beams. Now, electron beams are important in a lot of ways, although I do have to say that they are kind of going the way of the dodo, and shortly they will be probably obsolete because we're working on high definition images and other ways to produce these kinds of things. But, for the last 50, 60, 70 years, electron beams have been the major way that we've produced images on a TV screen, for example. Now, with the high definition TVs and the flat screens and the computer monitors, it's a little bit different. But even the first computer monitors, the ones that weren't flat, if you've got an old monitor in your house or even an old TV, you notice that it's very deep. The screen is in front and it goes way back. And that's because the image was created by an electron beam. So how does this happen? Well, it starts with what we call thermoionic emissions. Okay, and essentially what this means is that when materials are heated, the temperature increases. Obviously, duh. But what that means is that the kinetic energy of the molecules increases, and of course, inside molecules, there are protons, electrons, and so on. And some of that kinetic energy gets transferred to the electrons. So the electrons are moving faster and faster and faster. Now, if we produce these high velocity electrons inside what we call a vacuum tube, we can do all sorts of wonderful things with it. Now, a vacuum tube is just a sealed, typically glass tube with most of the gases removed. So it's a vacuum, right? Just like outer space. There's no air in there. And what you do is you run an electric current through a very thin filament, almost like a light bulb, and the filament becomes positive. And the electrons that are emitted from the molecules are then attracted back. All right. And if you adjust the voltage a little bit, you can reach what we call an equilibrium, where the electrons are moving, or eventually, if we change the magnetic field, we can actually get the electrons to stand still. And the rate of the emission of the electrons is completely dependent upon how hot the filament becomes. The hotter it becomes, the more electrons are released. So what does this mean in terms of practical technology? What can we do with this information? Well, there's a great deal of stuff, but before we get to that, let's talk a little bit about the algebra, the mathematics behind this. We know, of course, that the electromagnetic force, is equal to the electric field intensity times the charge. That's this formula, and we learned about this in the last unit. In addition, we know that the electric field intensity is equal to the potential difference divided by the distance between the positive test charge and the charged object we're talking about. And if we combine these two formulas, we get this. The electric force is equal to the potential difference times the charge divided by the distance. Now this is essentially around a positive charge. And so if we have an electric field going off in these directions. Remember, the arrows point in the direction of what would happen to a positive test charge. But notice that the density of the field lines is greater here than it is here. So the electric field gets weaker as we get away, as we go further away. However, if we have two parallel plates where one side is positive and the other side is negative, and we stick an electron in the middle, the field is, the density of the field is constant. All right, there's the same difference between here as here and so on. And so an electron in a field between two parallel plates will be accelerated toward the positive plate, but the field is constant, and that's key. Right, keeping that magnetic field constant by making sure that the two plates are truly parallel to one another. Now, if we can create an electron beam between two parallel plates, we can actually then create images using that technology. And so what we do is we create what's called an electron gun. I know this, for some reason, this picture is very fuzzy, but this is what we call an electron gun. And what that is a positively charged anode placed near the cathode in a vacuum tube. So this whole thing here is a vacuum tube. This whole thing is a vacuum tube. And so if we heat the filament up and create a high velocity, a bunch of high velocity electrons, if we place a magnet, and that's what this is, it's a scanning magnet or scan magnet, I think. What we do is we form what's called an electron gun. So the electrons are basically firing out of the cathode and into the vacuum tube. But by manipulating the voltage running through the parallel plates, we can then focus that beam of electrons so that we can send it this way or whatever. All right, so let's talk about how we control this. The electron beam itself can be controlled one of two different ways. We can use what we call electrostatic control using the parallel plate idea. All right, but we can also use a set of magnets, and here we're going to use the third left-hand rule. Right, remember, hold your left hand out, and the fingers point in the direction of the magnetic field. The thumb points in the direction of the electron flow, and the palm faces is the direction of the magnetic force. And so that comes down or back down to this idea, where the magnetic force here is equal to the charge times the velocity times the magnitude of the magnetic field. Okay, that's what B is in this case, the magnitude of the magnetic field. All right, so force equals charge times velocity of electrons times the magnitude of the electric field. I'm sorry. Start that again. The magnetic field in this case. All right, charge, velocity, magnetic field. So that brings us to an example problem. Now, again, there's no homework on this unit. I'm not even going to quiz you algebraically on this unit. We'll talk about Friday's quiz at the end of this lesson. But let's say we have an electron traveling at a constant speed of 2.0 times 10 to the 7th meters per second. And it enters a uniform magnetic field of 1.0 times 10 to the negative 4th Tesla. All right, well, we have then the velocity of 2.0 times 10 to the 7th. The magnetic field is 4.0 times 10 to the negative 4th. And I want to know the magnitude of the magnetic force. All right, so that's my big fat question mark. Well, the other thing that we know, or we need to know, because remember, F equals Q times V times B. And we know that the charge on a given electron is 1.6 times 10 to the negative 19th. All right. So I'm not going to write all these numbers out again, but in this case, the force is going to be now 1.6 times 2 is 3.2, and 3.2 times 4 is 12.8. So 12.8, and then multiply that by 10 to the 7th times 10 to the negative 4th is 10 to the 3rd, and 10 to the 3rd times 10 to the negative 19th is 10 to the negative 16th. And now, of course, we have to put this back into scientific notation. We make the number smaller, we make the exponent bigger. It becomes 1.28 times 10 to the negative 17th newtons. Okay? So 1.2, actually, with sig figs, it would be 1.3 times 10 to the negative 17th newtons. Okay. Anyway, so we can calculate the amount of force necessary to send a beam of electrons in a given direction.
It's 9 o'clock.
Well, thank you, Jesus. Now, this brings us to a discussion of a technology that is rapidly becoming obsolete, and that is a cathode ray tube. If you've got an old TV in your house or even an old computer monitor, this is how that thing produces an image. All right. We start out with a fluorescent screen on the outside, and notice that it's got a concave shape. It curves around. Whoops. Anyway, so we have on this thing not only the fluorescent screen, but notice that we've got a cathode with a heater coil in it, and that is producing these high velocity electrons. We then run it through past and the dotted line represents the electron beam. The anodes are located here and here and here, and what they're doing is using an electric field to focus the beam. And then you've got two sets of magnets, a focusing coil and a deflecting coil here. And so the focusing coil brings the beam together so that it's not spread out as it travels through the tube. And then the deflecting coil causes that beam to curve off into a specific direction. And so the way that an image was produced in one of these things is that the beam of electrons sweeps across the field and back and forth and back and forth and back and forth. And each of these beams, depending upon its intensity and strength, it carries information about the brightness and intensity of each of the primary colors, the blues, the greens, and the reds. Okay, and so what you do is you could produce a color image on essentially a curved glass lens, and that's how an old TV screen used to work. All right. Nowadays, the flat screen TVs and the plasma TVs and that's different technology. So don't be confused by that. Okay. So what else do we do, or what else can we do with these charged particle beams, whether they be electrons or protons or anything else for that matter? Well, those of you who took chemistry last year with Mr. Leonard or are planning on taking AP chemistry may talk about something called a mass spectrometer. And what you can do with a mass spectrometer is actually measure the mass of an individual atom, believe it or not, because you can study its ions inside a magnetic field. And so what you do is you vaporize the element by heating it to very, very high temperatures. The electrons are stripped from that atom, creating ions, and then the positively charged ions are fired through a set of electric fields and magnetic fields, just like we did with the cathode ray tube in the previous slide. All right, and the electric field and the magnetic field are perpendicular to one another. What happens there? Well, here's the deal. For an electric field, we know that the field strength is equal to the field intensity times the charge of the particle in it. And for a magnetic field, we know that the force is equal to the charge times the velocity of the charged particles times the strength of the magnetic field. Now, if we set those two forces equal to one another, we get the electric force equal to the magnetic force. Notice that the charge cancels out, so it doesn't actually matter whether it's a single electron or a charged particle with 10 protons or whatever it happens to be. And so we can reduce that equation down to the electric field intensity equals the velocity of the particles times the magnetic field strength. And then we can actually calculate the velocity. How fast are these charged particles moving? Based on that, we can then calculate how fast what the mass of the particle that's actually traveling. The faster the particles, the lighter the particles. Okay. And so what we can do then with the information that we calculate in that previous calculation is once we've burned up that element and sent it through, we can then figure out, because of its mass, we know what its velocity will be, because it's all proportional. Again, the lighter it is, the faster it will actually travel. So the ion travels through the two fields, the electric field and the magnetic field, and then it enters another magnetic field, and it's deflected onto a photographic plate, all right, which is, again, old technology, but essentially it's typically a glass plate with fluorescent chemicals on it that will light up, essentially, when the beam actually hits it. And so since we're deflecting the beam, if the beam is traveling this way, it forms part of a circular path. And so, because if you were wondering, how do we figure out the mass from all this? Well, we set the QVB equal to the centripetal force equation. Get rid of one of the velocities on each side, and so Q equals m times v divided by r. If we rearrange this algebraically, we can actually use it to solve for the mass. Now, I didn't get rid of the velocities there, but it's Q times B times R over the velocity. So once we know the velocity, we can then figure out what the mass is as well. All right, and so this is how a mass spectrometer works in chemistry. Okay. Now, this technology was actually used to win the Nobel Prize in 1911 by Joe Millikan. And this is a very famous experiment. It's called the Oildrop Experiment. Essentially what he did, and we've talked about this before, but essentially what he did was he gave a bunch of oil droplets a negative charge. All right, and then he used an atomizer, which is like an old-fashioned perfume bottle, to spritz little droplets of that oil into a chamber. And at the bottom of the chamber was a positively charged plate, and at the bottom below that was a negatively charged plate. So an electron would come and fall through this little opening, and then he would adjust the voltage, so the electrostatic force, versus the force of gravity. And so he was able to calculate the charge on each of these little particles that he had. And he didn't get 1.60 times 10 to the negative 19th for any of them, but what he did find was that they were all multiples of 1.6 times 10 to the negative 19th coulombs. And so therefore, he was able to calculate the elementary charge, or the charge on a single electron, and therefore also the charge on a single proton, as 1.60 times 10 to the negative 19th coulombs. Okay. Now, this is the last thing that I want to talk about is something that's kind of almost science fiction. But starting in the mid-1950s, a group of European scientists developed a compound in Switzerland, right on the French border, called CERN. And I can't remember what it stands for in French, but essentially the N is for nuclear and the R is for research. So nuclear research. And what they did was they built a bunch of very large particle accelerators. The biggest one, the Large Hadron Collider, is actually 27 kilometers in circumference. All right, so imagine a circle 27 kilometers in circumference, and they fire charged particles around this thing using a series of magnetic fields and electric fields to focus these beams. And they've made all sorts of fascinating discoveries. They've discovered all sorts of not only atomic particles, but even particles that are smaller than protons and electrons and neutrons. And they do all sorts of other research as well. The World Wide Web, the WWW, was invented at CERN. So, and CERN made it free to everyone, which is why we have the internet today. So there's all sorts of research going on there, not just particle acceleration. In any event, so that's just a brief summary of moving charged particles through electric and magnetic fields and some of the applications that we can use for them. So, happy Tuesday. We are going to, the quiz Friday is going to cover combined circuits, all right? And I'm going to post a couple of practice problems for that on the probably tomorrow's topics page. All right, have yourselves a lovely, lovely day. There we go.